Good morning, class. Yesterday we started talking about solutions. We defined the three different types of solutions. We were really just getting into the introduction, talking about how you have a solute dissolving in a solvent, and then you make a certain type of solution. So today we're going to look at a few more calculations with solutions, and the first we are going to look at is what is called molarity. Molarity is abbreviated with a capital M. And molarity, by definition, is the number of moles of solute dissolved in 1 liter of solution. So whatever is being dissolved, typically this is the solid, how many moles of that per liter of solution. Now sometimes this is also called molar concentration, but it's referring to the same thing. So if we were to set up an equation for molarity, molarity equals the moles of solute divided by the liters of solution. Now the key to this, the molarity equals moles, it must be in moles. So if you have a value in grams, you need to do a conversion. In liters, the volume must be in liters. Remember, they're in 1 liter, this is 1,000 milliliters if you don't remember your metric prefixes. Okay, so the volume must be in liters. So let's start with a simple example, and then we'll do a few more other examples. So first you're asked to find the molarity of a solution that is made with 0.50 moles of sodium chloride and 0.1 liters of solution. Okay, now this one's pretty simple. We know our molarity equals, we have 0.50 moles of our sodium chloride, and then we have 0.1 liter of solution. So 0.5 over 0.1 is just 5, and we have 2 significant figures and also 2. So this would be a 5.0 molar solution of our sodium chloride. Okay, now in lab a lot of times we use concentrations that are 1 molar or less. They aren't as concentrated, so for the most part they aren't as dangerous as the higher concentrations. So if you are already given moles and liters, the calculation is very simple. Let's look at another one. Example 2 says intravenous IV saline solutions. So if you have to be hooked up to an IV if you're at the hospital, those typically contain 0.90 grams of sodium chloride in 100 milliliters of solution. We're asked the molarity. Okay. So we know molarity is moles over liters. We don't have moles and we don't have liters, so we need to do some conversions first. We've learned in the last couple units we know how to get mass to moles by just using the molar mass. Alright, so if you add up the atomic mass of sodium, which is 22.99, plus chlorine, which is 35.45, you get 58.44 grams of sodium chloride for every 1 mole. We divide so the gram unit cancels, and then we should round to 3 significant digits, so 0.015 moles of NaCl. So we know how many moles this is. Okay, now if we have 100 milliliters, if we divide by 1,000, this would be just 0.100 liters. So our molarity, if we're just dividing by 0.1, we're just moving the decimal. So our final answer would be 0.15 molar solution of our NaCl. Okay, and if you notice, this solution is not very concentrated relative to our first example when we got 5 molar. So this one again was just showing a conversion of mass to moles and then making sure you had moles and liters. Right, now example 3 is a little bit different because it gives you the molarity. Okay, so we are asked how many grams of potassium phosphate would be needed to make 200 milliliters of a 0.5 molar solution. So this time we know the left side of the fraction. We know the molarity is 0.5, but we don't know the number of moles, and we have 200 milliliters, so if you divide by 1,000, we get 0.2 liters. Okay, so if we multiply, we can get the number of moles, but the question wants grams. So first, if you just take 0.5 times 0.2, the number of moles will just be 0.1 and 0, 0, since 3 significant figures and 4. So this is 0.100 moles of potassium phosphate. Okay, this would require your ion sheet. K is positive, phosphate is 3 negative, so crisscross, we get K3PO4. Now if we have moles, we need the molar mass. So 1 mole of K3PO4. Add up the atomic masses. So 3 times 39.1 plus 30.97 plus 64, because 4 times 16, and we get 212.27 grams. So 0.1 times this, we just move the decimal 1 spot, so 21.2 grams of potassium phosphate. Okay, now why is this helpful? If you wanted to actually make this solution, this is the mass you would get of your solute, and then you would dissolve this in water to get to the volume of 200 milliliters. Okay, that's what we will be doing in the lab. We're actually going to make the solution. So you have to know that this is the solute you would have to mass. You add it to a beaker and add water up to 200 milliliters, stir it up, and then there's your 0.5 molar solution of potassium phosphate. Okay, finally, example 4 is about Kool-Aid, which will definitely pertain to the lab since we're going to make 3 different concentrations of that. So if you want to make Kool-Aid that has 150 grams of sucrose or sugar dissolved in 1 liter of water, it wants the molarity. Okay, well, we know molarity is moles over liters. We know it's 1 liter of water. So we want to figure out how many moles this would be, so we need to get 150 grams to moles first. So take a second and add up the molar mass. So 12 times 12.01 plus 22 times 1.01 plus 11 times 16. We get 342.34 grams. So if we divide these numbers, we get 0.4382 moles of our sucrose. If we plug that in the equation, we see we are just dividing by 1, so then our answer would be a 0.4382 molar solution of Kool-Aid. Alright, so in the lab again, we're going to have to make these solutions. So I will give you different molarities and the volumes, so you'll have to figure out what mass of the solute of the sugar that you will have to add to make these solutions. Okay, if you have any questions with molarity calculations, just let me know.